right? What the expression we got? Pressure was 1 by 3 N by capital V small m into V square bar. Now what is V is the volume, then your N is the number of molecules, small m is the mass of each molecule, and V square bar is the mean square velocity, right? So now from this on this particular expression, we are going to move forward, right? And the next, let me put on the next slide, right? Okay. Now here what we are going to do is we are going to interpret the interpretation of temperature of the kinetic theory, right? Okay. Now this particular, let me talk about this expression. This is the expression P is equal to 1 by 3 N by V M C square bar is what I told you, right? Okay. Now what we are going to do is shift this volume on the left hand side and I get this expression. Okay. Now I'm multiplying by 2, dividing by 2. Why am I doing all this? Because I want to get the expression for kinetic energy. I'm going to relate kinetic energy and temperature. That is what I'm going to do, right? So in order to get expression for kinetic energy, I'm doing some rearrangement. I know the formula for kinetic energy is half mv square bar, right? So half mv square. Okay. So this is the formula for kinetic energy, and that is why I am multiplying and dividing the expression by 2, right? So if I multiply and divide by 2, I am left with 2 by 3 N. This is one factor, and this is your kinetic energy, right? So the quantity half mv square bar is the average. Now remember, this is translational kinetic energy. Yesterday we spoke about the particle that is there, or the gas molecule that is there inside the container. It is moving along the x, y, x, z direction, and that is the translational kinetic energy that I'm talking about. Okay. Now, if I'm talking about an ideal gas, in an ideal gas, the molecules, you have done this in 11th standard chemistry also, that the molecules are non-interacting. If they are interacting, I call it as a real gas, right? Now, if the molecules are non-interacting, then there is no potential energy. Let me talk about this particular fact a little bit, right? If I'm talking about the gravitational potential energy, why does the gravitational potential energy is there? If I'm talking about Earth and any object near the Earth, the gravitational potential energy is because of the force of attraction that is there between the Earth and that particular body, right? So that is the gravitational potential energy. Let me talk about another example we did was your electric potential energy. Electric potential energy exists because there is a force between those two charged particles, right? Now here I'm talking about the molecules not having any interaction with each other, right? That is why, because the molecules are not having any kind of interaction with each other, what happens is there is no potential energy term. Whatever energy is there possessed, internal energy possessed by that body, that is only the kinetic energy. By those gas molecules, it is only the kinetic energy. Now we are going to try and find out the average kinetic energy, right? So the total, I can replace this entire term. M is the mass of one molecule. So this is the kinetic energy of one molecule. If I multiply it by N, then I will get kinetic energy for all those N molecules of gas that are there in our container, right? So I can write the energy as N into half mv square. But what is N into half mv square? This N into half mv square, if I replace this particular term here, what will I get? PV is equal to 2 by 3, and this is nothing but the energy of those, kinetic energy of those N molecules. So I am replacing it by E alphabet, right? And I also know yesterday's expression, I told you to write down the ideal gas equation in terms of Boltzmann constant. It is N kb into T, right? So I can write this E as 2 by 3 as N kb into T, or I can write E as 3 by 2 N kb into T, right? Now this is the energy that kinetic energy that is there for those n molecules. If I want to find out the average energy per molecule for one molecule, I will have to divide it by the number of molecules. So if I divide this E by N, I will get the kinetic energy per molecule, average kinetic energy per molecule. And why I'm saying kinetic energy? Because in an ideal gas, potential energy term doesn't exist. Further, when we move, we are going to talk about a situation where the potential energy is also there, right? So kinetic energy or the average energy per molecule, if I write it is E by N is equal to 3 by 2. This is a Boltzmann constant, it is a constant. So it is directly related to the absolute temperature of the gas. The more the temperature, the more the kinetic energy per molecule. That is for sure. Internal energy of the system goes on increasing if I go on increasing the temperature. Let me move on to the next slide. Right. Okay. Now this is the objective that is there in your book. In an ideal gas, the molecules possess. Just now we saw, right? Just now. It is only kinetic energy, both kinetic and potential, only potential, neither kinetic nor potential. All of you all I know the answer, right? Just now I said that potential energy doesn't exist. It is only the kinetic energy. I'm talking about an ideal gas. Let me move on to the next numerical. Now here I'm supposed to find out the kinetic energy, right? The average kinetic energy in terms of per kilomole, right? Average kinetic energy per kilomole. I have to find it out per kg. I have to find it out per molecule of oxygen, which is at 127 degrees Celsius, right? So first thing is I'm going to convert this into absolute temperature plus 273 I'm going to do. Then what else I am given? Molecular weight of oxygen is given as 32 and R is given to me. This R is given to me in joule per mole Kelvin. The first answer that I have to do is per kilomole, right? So I am going to convert this into kilomole, right? Per kilomole, I'm going to convert this instead of mole, I'm going to use kilomole, right? Avogadro's number is also given, right? These are all the things that are given to me. This is what I have done, converted into joule per kilomole because I need my answer for kinetic energy per kilomole, right? Now let me go to the expression for this is the expression I had. Just now we wrote down this expression, spoke about this expression. Now here I'm doing some rearrangement. This is nothing but the kinetic energy, 2 by 3 kinetic energy, right? Instead of PV, I can substitute it as nRT. So kinetic energy I can write as 3 by 2 PV or I can write it as 3 by 2 nRT. Now I want kinetic energy per mole. So N is the number of moles, right? So if I make the value of N as 1, I will get the kinetic energy per mole. If I take this N and put it here, I'm going to get kinetic energy per mole. So what is the formula for it? 3RT by 2, right? So this is the expression and you are put the values and you are going to get this expression for kinetic energy per kilomole. This is the answer. Now the next thing that we have to do is we have to find out kinetic energy per kg, right? Next thing is kinetic energy per kg. Okay. Now what is the formula for kinetic energy per kg? It is kinetic energy per mole divided by the molecular weight, right? Molecular weight is nothing but your Avogadro's number multiplied by that mass, right? Okay. So I put down the values, the molecular weight is given to me, I can get the kinetic energy per kg. Next is I have to find out kinetic energy per molecule, right? Per molecule of oxygen. Okay. Now what is kinetic energy per molecule? I'm going to, in 1 mole, how many molecules are there? It is equal to the Avogadro's number. So if you have kinetic energy per mole, if I'm talking about 1 mole, then if I want to find out kinetic energy per molecule, I have to divide it by the Avogadro's number and I will get kinetic energy per molecule, right? So this is the numerical number 18 from your textbook. Now let us talk about the next very important fact, and I'm going to need a lot tomorrow also. All this what we are going to do right now, right? So tomorrow again we are going to need all of this. So just see to it that you have understood all this. Okay. Now I'm talking about law of equipartition of energy. As the name suggests, the energy equipartition. That is, the energy is distributed equally in all the three directions. That is what it is going to indicate. Now, if I'm talking about a single molecule, I know that the kinetic energy is kinetic energy along x-axis plus kinetic energy along y-axis plus kinetic energy along z-axis. This is single molecule is moving in all the three dimensions, x, y, z coordinates, vx, vy, vz we saw yesterday. And for a given temperature, right? If for a given temperature, right, for a gas at a temperature T, the average kinetic energy is, this is the average kinetic energy. And just now, some time back, we found out the kinetic energy per molecule. We had written it down as capital E by capital L. And what answer we had got for capital E by capital L? The answer was 3 by 2 kb into T. Kb is the Boltzmann constant. That means the average, that is the mean kinetic energy per molecule is this much. Now, what is that equipartition? Law of equipartition of energy. This is the total energy that is there per molecule in all the three directions, x, y, z. So kinetic energy along x, y, z, I can represent it by the energy is distributed equally. So it is going to be half kBt along x, half kBt along y, half kBt along z, and this is your kinetic energy, the mean energy associated with every component of translational kinetic energy is half kBt, right? 3 by 2 kBt was the total energy per molecule that we had, all the three axes or all the three motions taken into consideration along x, y, z. And for a particular direction, only x, only y, only z, it is half kBt. This expression you have to remember, right? Total energy contribution of the molecule is 3 by 2 kBt, but along one particular direction it is 1 by 2 kBt. Now here what we have is the this is true. The law of equipartition of energy is true when I'm talking about the temperatures which are high. It is not applicable for low temperature. Then I have to look into a lot of details. There are various things that come into play. So it is not applicable for low temperatures. Let me move on to the next slide. Right. Now basically here the heading is degrees of freedom. Now what do I mean by degrees of freedom? I'm talking about this particular aeroplane, right? This particular aeroplane can move in this direction, that is towards the left. It can go towards the right. It can go up. It can go down. This is not all. It can roll about its nose, rolling movement, right? It can have a pitching movement. These are its wings, right? It can have the pitching movement, and it can also yaw about its vertical axis, right? This movement about the vertical axis, the term used is yaw. So these are the movement. This is how an aeroplane can move. It can go left, it can go right, it can go top, it can go bottom, it can come out of the screen, it can get inside the screen. Also, it can do rolling, it can do pitching, and it can yawing. It can do yawing, right? These are the three additional movements that are there, and three movements along x direction, along y direction, along z direction, right? So this is an example of what is the freedom of movement of this particular aeroplane. Now let me get back to the molecule, right? Now if I am talking about a molecule and that molecule is moving in a straight line, right? If I want to find out the position of the molecule at any particular instant of time, or if I want to describe its location and I want to study its motion, then I need only one particular coordinate. If it is moving along x-axis, I need only x coordinate. Let me say that the molecule is moving in a plane, right? It is moving in a plane, say in the xy plane. Then if I have to describe its motion, if I have to describe its location, if I have to track that particular point, then I need two coordinates. One is the x coordinate and the y coordinate. If it is moving in the YZ plane, I need y coordinate and z coordinate. If it is moving in the XZ plane, I need the x coordinate and the z coordinate, right? Now, if I'm talking about movement of a particle in space, when we spoke about the expression for pressure, right, of the gas held in that container, I was the gas was held in the container, and the gas was free to move, actually Brownian motion, in all possible directions, three-dimensional motion. Right. So when it is moving in space, the three coordinates are required. If I want to find out its location, where it is located, or what is its motion, that is Vx, velocity along x direction, y direction, z direction, all that, for that I need three coordinates. Right. So degrees of freedom of a system are defined as the total number of coordinates or independent quantities required to describe the position and configuration of the system completely. If I want to describe the position and configuration, I'm going to talk about kinetic energies, right? The particles are moving, they are not stationary. So I'm going to talk about the energies. So for that, what do I need is whatever number I need, what number of coordinates I need, or number of independent quantities I need, I call it as the, I call that particular thing as the degree of freedom. Okay. Now this degree of freedom, again tomorrow's class I'm going to need it one more time, right? Before like when after we end the class, I will send you a link. You can go through the YouTube particular video related to this degrees of freedom of various molecules. We are going to talk about those degrees of freedom in tomorrow's class, right? Okay. Let me move on to the next slide. Now I'm talking about a diatomic molecule. Now diatomic molecules, say oxygen, nitrogen, right? Now oxygen or nitrogen, diatomic molecules, two molecules. Now basically I'm talking about the diatomic molecule. Now this is the molecule. There is an oxygen atom here, oxygen atom here. There is a covalent bond formed by sharing of two electrons, right? So this particular molecule can move along the z-axis up and down, right? It can move left and right along the x-axis, and it can move along the y-axis, that is inside the screen and coming out of the screen. So it has three translational motions. It is going to move along the x-axis, or it can move along the y-axis, or it can move along the z-axis. So this molecule, I say, has three translational degrees of freedom, right? It can move along your x, y, and z axis, three translational degrees of freedom. Now this molecule also can rotate, right? It can rotate about its center of mass, right? Let me talk about this molecule. It can rotate about the z axis. So this is how it is going to rotate about the z axis, right? This is the way. Then it can rotate about your y axis also. So it can rotate about the y axis in this particular manner. It can also, this is the, they have shown this movement about the z-axis. This is the movement about the y-axis, and it is stationed along the x-axis, let me say, and the center of mass is at the origin. And when somebody, mic is not, Abhijit, mic. Okay, right. So when the particle is stationed here, the center of mass is at the origin. This is about the along the x-axis. Now the particle can also, the molecule can also rotate about the x-axis like this, round and round and round. But then for this, what kinetic energy I'm going to talk about? I'm going to talk about rotational kinetic energy. And when the particle is moving round and round like this about this x-axis, actually the nucleus 10 raised to minus 5, very, very small size. And if I try to find out this, what to say, the rotational kinetic energy, half I omega square, I for that body is 2 by 5, because it is a sphere, 2 by 5 mr square. So r is very, very small. That is why it is going to be very, 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 very small about the x-axis, right? I is going to be very small about the x-axis. That is why I don't take that into consideration, right? So it has rotational degrees of freedom, but only two rotational degrees of freedom. There are only two rotational degrees of freedom, one along the y-axis and one along the z-axis, if this molecule is stationed on the x-axis, right? So what is the total energy? It is the translational energy plus the rotational energy. And this translational energy is half mvx square plus half mvy square plus half mvz square. And the rotational energy is half Iy omega y square. Remember this we did in rotational dynamics first chapter. Half I omega square is a rotational kinetic energy, and it is along the z axis as well. So this particular fellow, in all it has 5 degrees of freedom if I'm talking about oxygen molecule, or if I'm talking about a nitrogen molecule. Now I call this as a rigid molecule, right? Rigid molecule. Just remember the word rigid molecule. Each term is going to contribute half kBt, half kBt, half kBt, half kBt, half kBt, right? So the total energy is going to be 5 by 2 kBt. I need this tomorrow's class again. So again and again I'm repeating, if I'm talking about a diatomic rigid molecule, it has total 5 degrees of freedom. Every particular direction, what is the contribution of kinetic energy? It is half kBt. So along the 5 directions, right, it's going to be 5 by 2 kBt. Let me move on to the next slide. Right, now here I'm talking about non-rigid molecule, right? Non-rigid molecule means it can vibrate. Rigid molecule is the one where the vibrations are not taken into consideration, or there are no vibrations there. So I'm talking about a non-rigid molecule. They have said a real diatomic molecule. It contains those covalent bonds are there, and there is a possibility of the vibrations, right? So in addition to your translational, rotational, there is also going to be vibrational kinetic energy, right? There is going to be vibrational kinetic energy as well. Now, when I'm talking about vibrations, I'm talking about here real diatomic molecule, right? Real diatomic molecule. When I use the word, I am going to talk about potential energy as well, right? Okay. Now it has these molecules perform vibrational motion. Additional thing is vibrational motion. Translational degrees of the kinetic energy is along the translational, rotational kinetic energy and vibrational kinetic energy. Right. Vibrational kinetic energy consists, vibrational energy due to the vibration consists of the kinetic energy term and the potential energy term. Now this E is not only kinetic energy from now on, right? It is energy that is possessed with that particular molecule. It can be kinetic, and because it is vibrating, there is also a contribution of the potential energy. Now, how do I write down vibrational kinetic energy? Half mu is the velocity, so half mu square. And this term, if you remember, we have done this particular expression, potential energy, oscillatory motion, right? In oscillatory motion, we found out the potential energy. And instead of R, we had used X there. That is the only difference. Half kx square is what we had used, right? So, for a non-rigid diatomic molecule, the mean kinetic energy associated with the translational motion is 3 into half kBt. 3, I think I am clear about this 3 because x-axis, y-axis, z-axis, right? Then rotational motions are 2. There is rotational motion around the y-axis, around the z-axis. Also, there is rotational motion about the x-axis, but I told you that the rotational motion about the x-axis is very, 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 very less, right? That is why we are not going to take that into consideration. So I'm going to take only 2 degrees of freedom. So this is the energy associated with your movement along the rotational motion, for the rotational motion. Vibrational energy. Now this is not kinetic contribution, kinetic and potential. It is again 2 into half kBt. These are the one set of vibrations that are shown. I can have another set of vibrations in this way also. So the vibrational back and forth, it can be in and out also, right? So this is the vibrational energy, right? Let me move on to the next slide. Okay. Very important thing now, because in the next class we have to continue with this, all this vibrational, rotational, total degrees of freedom, kinetic energy, contribution of each term, half kBt and so on, right? Okay, now specific heat capacity. Remember in 11th standard we have done this. What is specific heat capacity? Let me tell you the definition, what it is. If I take 1 gram or 1 kilogram of a substance and I heat it, right? And the temperature of that particular substance is say 27 degrees Celsius. And I want to raise the temperature to 28 by 1 degree, right? So whatever is the heat required to raise the temperature of 1 gram of substance by 1 degree Celsius, right? 1 kilogram of substance, 1 gram of substance by 1 degree Celsius, I call that as the specific heat capacity, right? And the word that I use is principal specific heat capacity. And I'm going to talk about two terms. One is principal specific heat capacity. We have done this in 11th standard. And the other is molar specific heat capacity. When I'm talking about principal specific heat capacity, I'm talking about the quantity of substance in terms of kilograms, grams, right? And when I'm talking about molar heat capacity, I'm talking about the substance in terms of moles. I'm going to consider moles of substance, right? Now, molar specific heat capacity is denoted by the alphabet C, and principal specific heat capacity is denoted by the alphabet S, right? Now, when I'm talking about a gas, I have two specific heat capacities, especially for gases, right? Two specific heat capacities. What are the two specific heat capacities? In one case, I'm going to keep the volume of that gas constant. I know P, V, and T, right? So I can keep the pressure constant, volume changes, volume constant, pressure changes, and I'm going to do this in relation to the temperature, right? Okay, the changes happen because of the temperature, because of the heat energy that is supplied. So I have specific heat, molar specific heat capacity at constant volume CV, and at constant pressure it is given by CP. And we are going to find out this Mayr's relation is what we are going to derive. We are going to consider a mole of an ideal gas is kept in a cylinder and there is a piston fixed. Now I'm going to do two processes. In the first process, I'm going to keep the volume constant. I'm going to heat up the gas, right? The temperature is going to rise, but the volume is going to remain constant. That is, the piston is not going to change its place, right? Piston is not going to change its place. It is wherever it is, the volume is going to remain constant. Whatever heat I'm supplying, right, to raise the temperature, that heat is used only to increase the internal energy of that particular gas. No work is going to be done because the piston is not moving. No work is done. So whatever heat you have supplied, that heat is used only for raising the internal energy, right? Or I can write down dq minus dE. dE is the internal energy. dq1 is the heat that amount of heat that you've supplied, that is equal to CV into dt. Now, how did I get this? What is CV? Amount of heat required to raise the temperature of unit mass of that particular substance, 1 mole of that substance by 1 degree Celsius. But I'm not raising it by 1 degree. I'm raising it by, the temperature is rising by dt. So it is going to be CV into dt. Now, in the second case, what I do is I take this particular gas and I am going to keep the pressure constant, right? Pressure constant. That means the piston is able to move. So whenever I supply the heat energy, of course, the internal energy is going to increase. What is internal energy? The kinetic energy. That is going to increase. And at the same time, PDV, work done. Work is going to be done. PDV. Now, work done is force into displacement. Force is, force into displacement. And force is nothing but pressure into area. So if I do that calculation, it is nothing but PDV, right? Just if you rearrange, work is force into displacement. Force is pressure multiplied by area, right? Pressure multiplied by area multiplied by displacement. What am I going to get? Area into displacement, I'm going to get the volume. Somebody is doing annotations. Please stop that, right? Please stop the annotations. Okay, right. So we are going to talk about this PDV. Okay, right. Now, this is the increase in the volume. This is the work done. Work is going to be done. So it is not only increase in internal energy, but there is going to be work is going to be done. So what can I write? This is nothing but your Cp into dt. Again, same amount of heat required to raise the temperature of unit mass of substance by 1 degree. Now we are not raising by 1 degree, we are raising it by dt. Temperature is rising by dt, so it is going to Cp into dt. So I can write down this Cp dt as, how did I get this Cv dt? This is dq minus d. This is Cv dt. So I'm going to have this as Cv dt, that is the internal energy. Please stop. Okay, so if I rearrange, I'm going to get this particular expression, or if I do this, PdV is going to, or I can write P into V is nRT, right? 1 mole of gas I've considered. So N is 1, so R into, so because the volume has changed, right? Volume has changed dV. It's because of the change in the temperature. Pressure we have kept constant. PdV is equal to RdT. So instead of this PdV, I can replace it by RdT. dt will get cancelled, and I'm left with Cp minus Cv is equal to R. Or the Mayer's relation, I can say this is, if I want to write it in terms of calories, right? Heat in calories and work done is in joules, then I can have this expression as R by G, right? If I want to do the conversion. Also, I can write down this particular expression in terms of the principal specific heats. I told you that your Cp is the molar specific heat and Sp is your principal specific heat. Now, how they are related to each other? They're related by the molar mass, right? So, if I substitute MO into Sp instead of Cp and MO into Sp instead of Cv, I can get the expression difference, or the Mayer's relation, difference in the specific heat at constant pressure and constant volume in terms of principal specific heats. This is the answer that I get. Always remember your Cp is going to be greater than Cv, because when the heat is supplied at constant pressure, work is also done and internal energy is increased. And when we are doing it at constant volume, only internal energy is increased. The work is not done. So naturally Cp is greater than Cv, right? Okay. Now this is the expression. Now yesterday's, let me get to yesterday's objective. Right. There we had done all this, right? Now here, this is the place, right? 10 by 9, directly we had written 11.11% as the increase, right? Okay, now this is the volume that is there after the pressure has changed, and this is what we get. Now if I want to find out the increase in volume, initial volume is V, now the volume has become this much, so the increase in volume is 0.111, and that is why the percentage increase comes out to be 11.11%. The percentage increase comes out to be 11.11%. Okay, right. So in today's class, what all did we do? We spoke about the energy, that is the kinetic energy, translational kinetic energy per molecule. I got it as 3 by 2 kBT. Right? And what does the equipartition theorem say? That the energy is distributed equally in all the directions, and that is why along x, y, z, I get it as 1 by 2 kBT. Then we spoke about the degrees of freedom. What is, if I want to locate, or if I want to study the motion of particular body, I need some coordinates, some independent variables, and how many? That is the degrees of freedom, right? So if I am talking about monoatomic molecule, we will divide them into monoatomic, diatomic, and polyatomic, say more than 2, right? So in case of monoatomic molecule, the molecule is not going to have rotational motion, or rotational motion. I told you, if the molecule rotates about its own axis, the rotational kinetic energy is very, very, very small, negligible. That is why if I'm talking about a monoatomic molecule, then you are going to have only the translational kinetic energy and the degrees of freedom along the translation. 3 degrees of freedom it is going to have. If I'm talking about a diatomic molecule, and if it is a rigid molecule, that means no vibrations, then it is going to have 3 translational degrees of freedom, of course, along x-axis, y-axis, and z-axis, and also it is going to rotate about 2 more axes along which it is not oriented, right? So I told you, if the body is along the x-axis, the rotation about the x-axis is, the energy that you get is very, 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 very small, so it is negligible, right? So we have 2 rotational degrees of freedom. And if I'm talking about a non-rigid molecule, that is the vibrations are also possible, then in that case there are additional vibrational degrees of freedom. So whenever I'm talking about a polyatomic molecule, I am going to have rotational, translational, and vibrational degrees of freedom, right? Okay. Right. Now, this is what I spoke about all the time, right? Monoatomic molecule. If I'm talking about a monoatomic molecule, then in that particular case, right, in case of the monoatomic gas, a gas contains any, let me say, Avogadro's number of atoms, and each atom has only 3 degrees of freedom, 3 translational degrees of freedom. And now here I have to remember the Mayer's relation as well. What is the Mayer's relation? Cp minus Cv is equal to R. Cp minus Cv is R. So I'm going to have, for monoatomic gas molecule, the average kinetic energy per atom, 3 by 2 kBT, of course. And what is the internal energy per molecule? If I'm talking about per molecule, it is going to be Na, Avogadro's number of molecules we have taken, Kb into dt, right? And if I find out Cv, that is the specific molar specific heat at constant volume, it is nothing but change in internal energy per unit time. I'm going to get this expression, and that is going to be 3 by 2 R. So if I substitute it here, I will get the answer for Cp. Now, this is gamma, that is the ratio of specific heat at constant, molar specific heat at constant pressure to the ratio of molar specific heat at constant volume, and that comes out to be 5 by 3, right? Gamma is the ratio of specific heats at constant pressure and constant volume, that comes out to be 5 by 3. If I'm talking about a rigid gas molecule, then it has 3 translational and 2 rotational degrees of freedom, total 5. So the total energy is 5 by 2 Na kBT, right? And if I want to find out the specific heat, molar specific heat at constant volume, it is going to be dE by dt. I hope all of you all are getting why you are coming to this particular expression, right? Because whatever heat you supply is used for only to increase the internal energy, and the heat that you are supplying is not to raise only 1 degree, but you are raising the temperature by dt, right? So you are going to have dE by dt, and this is 5 by 2 R. I do the same thing and I get gamma as 7.